Imagine pointing the most powerful telescope humanity has ever built at a patch of sky so empty, so unremarkable, that it appears completely dark to the naked eye. What would you expect to find? Nothing, perhaps. A few faint stars? What if I told you that within that tiny, supposedly empty square of darkness lies one of the most profound discoveries in all of human history? It's a secret so vast it changed everything we thought we knew about the universe. Join me now as we gaze into the Hubble Deep Field, and together we will witness infinity itself. It is December 1995, and in the cold vacuum of space, the Hubble Space Telescope orbits silently above our world. This magnificent instrument, our eye on the cosmos, has already shown us wonders beyond imagination. But now, astronomers are about to make a decision that many consider reckless, even foolish. They want to point Hubble at a region of sky near the Big Dipper that appears to contain absolutely nothing. No bright stars, no obvious galaxies, just darkness. For 10 consecutive days, Hubble will stare at this empty void, using precious observation time that could be spent on known, spectacular targets. Why would anyone waste such valuable resources on what appears to be nothing at all? The answer lies in a question that has haunted humanity since we first looked up at the stars. How big is the universe? How many galaxies exist beyond our own Milky Way? You see, we knew there were other galaxies out there, countless islands of stars scattered through the cosmic ocean. But we had only scratched the surface, capturing the brightest, closest ones. What about the faint, distant galaxies we could barely detect? What about the ones we could not see at all? The Deep Field project was born from a simple but audacious idea. If we stare long enough at seemingly empty space, if we collect every single photon of light over many days, what will the universe reveal to us? Think about that for a moment. Imagine standing in a completely dark room and waiting for your eyes to adjust. See? At first, you see nothing, but slowly, shapes begin to emerge from the darkness. Details reveal themselves. The longer you look, the more you see. This is exactly what Hubble was about to do with the universe itself. By pointing its sensitive instruments at this dark patch of sky and exposing its camera for days on end, astronomers hoped to catch the faintest whispers of light from the most distant galaxies in existence. Galaxies so far away that their light has been traveling toward us for billions of years. It was a gamble, yes, but one that would pay off in ways no one could have predicted. The chosen target was a tiny region in the constellation Ursa Major, less than 1/24 millionth of the entire sky. To put this in perspective, if you held a grain of sand at arm's length, that grain would cover an area of sky about the same size as the Hubble Deep Field. We are talking about an incredibly small slice of the heavens. Director Robert Williams championed this controversial project, dedicating his director's discretionary time to it despite skepticism from many in the scientific community. Some thought it was a waste. Others worried that the images would reveal nothing interesting at all. But Williams and his team believed in the power of looking deeper than anyone had looked before. They believed the universe had secrets to share. As December 1995 unfolded, Hubble began its vigil. Orbit after orbit, the telescope returned to the same coordinates, collecting light. Each exposure lasted 30 minutes to an hour, and over the course of 10 days, Hubble accumulated a total exposure time of more than 100 hours. 100 hours of staring at what most people would call nothing. Can you imagine the patience required? The faith. During this time, the telescope was unavailable for other observations, and the astronomy community held its breath. Back on Earth, scientists waited anxiously for the data to arrive, wondering if they would find anything at all. The universe, as always, was about to surprise us beyond our wildest dreams. Think about what it means to wait for light. Every photon captured by Hubble during those 10 days had been traveling through space for unimaginable spans of time. Some of these photons began their journey when the universe was young, when our Sun and Earth did not even exist. They crossed billions of light years of expanding space, threading through the cosmic web, avoiding collisions with dust and gas, until finally, after eons of travel, they arrived at Hubble's mirror. This was not just observation. This was cosmic archaeology. Each photon was a messenger from the ancient past, carrying information about galaxies that might not even exist anymore. We were about to receive messages from the dawn of time itself. As the observations concluded and the data began to be processed, the team assembled the individual exposures into a single, deep image. This is where the magic happens. By combining multiple exposures, you can reveal objects far too faint to see in any single image. It is like looking through layers of tissue paper, each one revealing a bit more detail beneath. The computers worked through the night, and slowly, pixel by pixel, the Hubble Deep Field began to take shape. What emerged from that processing would forever change how we see the universe and our place in it. The empty patch of sky was not empty at all. Not even close. It was teeming with galaxies, thousands of them scattered like jewels across the darkness. When the first complete image was revealed to the scientific team, there was stunned silence. Then awe. Then an overwhelming realization of what they were seeing. Where there should have been darkness, there was light. Where there should have been emptiness, there was cosmic abundance. The Hubble Deep Field contained not dozens, not hundreds, but approximately 3,000 galaxies in that tiny patch of sky. 3,000 entire galaxies, each containing hundreds of billions of stars, captured in an area smaller than a grain of sand held at arm's length. If this was what existed in one random, supposedly empty part of the universe, what did that mean for the whole sky? The implications were staggering, beautiful, and deeply humbling. Let us pause for a moment and truly absorb what this means. 3,000 galaxies. In a patch of sky you could cover with a pinhead. Now, imagine taking that grain of sand and moving it to another random part of the sky. And another. And another. The entire celestial sphere contains roughly 13 million such regions. If each one contains a similar number of galaxies, that means the observable universe contains more than 100 billion galaxies. 100 billion galaxies, each one a vast metropolis of stars, planets, and possibilities. The number is so large it becomes almost meaningless to our human minds. How do you comprehend such abundance? Such incredible, overwhelming richness. To put this in perspective, there are more galaxies in the universe than there are grains of sand on all the beaches on Earth. More galaxies than there are stars visible to your naked eye on the darkest night. The Hubble Deep Field showed us that we live in a universe so vast, so incomprehensibly full of structure and light, that our previous estimates were laughably conservative. We thought we understood the scale of the cosmos. We were wrong. Beautifully, wonderfully wrong. And here is the most astonishing part. These galaxies are not just sitting there in space. They are moving, evolving, living their lives across cosmic time. They are born, they grow, they collide, they transform. Each one is a dynamic, changing entity with its own history spanning billions of years. Now, look closely at the deep field image with me. Do you see how each galaxy has its own character, its own appearance? Some are perfect spirals with elegant, sweeping arms. Others are smooth ellipses glowing with a soft, ancient light. Still others are irregular, chaotic, barely holding together. There are galaxies that shine brilliant blue, indicating the fire of newly formed stars. Others glow with deep reds and oranges, the signature of older stellar populations. Each galaxy is unique, shaped by billions of years of evolution, by its own history of star formation and gravitational interactions. They are like cosmic fingerprints, no two exactly alike. What stories could these distant lights tell us if we could hear them? Some of the galaxies in the deep field are relatively nearby, cosmically speaking. They might be only a few 100 million light years away, their light reaching us from a time when dinosaurs were still beginning to evolve on Earth. But others, the faintest and most distant ones, are so far away that their light has been traveling for over 12 billion years. When that light began its journey, the universe itself was young, only 1 billion or so years old. The galaxies that emitted this ancient light appear small and irregular because they truly were smaller and more chaotic back then. We are seeing them as they were in their infancy, in the childhood of the cosmos. This is one of the most extraordinary aspects of astronomy. When we look out into space, we are simultaneously looking back in time. Light travels fast, but the universe is so vast that even light takes billions of years to cross cosmic distances. The Hubble Deep Field is not just a snapshot of different places in the universe, it is a timeline. A visual history book showing us how galaxies have changed and evolved over the entire age of the cosmos. The nearest galaxies show us what mature galaxies look like today. The most distant ones show us the early stages of galaxy formation. In a single image, we are witnessing the entire story of galactic evolution, from ancient chaos to modern order. Consider this profound truth. When you look at the deep field, you are not seeing these galaxies as they are right now. You are seeing them as they were when their light left them. Galaxy 12 billion light-years away appears to us as it existed 12 billion years ago. Right now, in real time, that galaxy has evolved, changed, perhaps merged with other galaxies. It might look completely different. Some of the stars you see in those distant galaxies have long since died and become black holes or neutron stars. New generations of stars have been born and died countless times. The universe we see is a cosmic ghost, an echo of the past. We are surrounded by ancient light, by the memory of what once was. And here is something that brings me a deep sense of peace. Despite the enormous distances involved, despite the billions of years of separation, we are connected to all of these galaxies. The same physical laws that govern the atoms in your body also govern the motion of stars in the most distant galaxy in the deep field. The same forces of gravity and electromagnetism, the same quantum mechanics, the same fundamental constants of nature. We are part of the same universe, made from the same cosmic fabric. When you look at the deep field, you are looking at family, distant cousins separated by time and space but bound together by the fundamental unity of the cosmos. The Hubble Deep Field image was released to the public in January 1996, and its impact was immediate and profound. Scientists were astonished. Educators were inspired. But perhaps most importantly, everyday people around the world were moved by what they saw. Here was proof, visual proof, that the universe is far grander, far more filled with wonder than we had dared to imagine. It became one of the most iconic images in the history of astronomy, appearing in textbooks, museums, and classrooms around the world. It reminded us that we are part of something incomprehensibly vast and beautiful. It gave us perspective, gave us humility, and yes, it gave us a profound, calming sense of awe. Now, let us focus our attention on specific types of galaxies within the deep field. Among the most beautiful and recognizable are the spiral galaxies. These cosmic pinwheels dominate our imagination when we think of galaxies. Our own Milky Way is a spiral galaxy, and when we see these elegant structures in the deep field, we are looking at siblings to our cosmic home. Spiral galaxies are characterized by their distinctive rotating disk of stars, gas, and dust, with gracefully curving arms that wind outward from a bright central bulge. They look like hurricanes frozen in time, or flowers blooming in the darkness. But what creates these mesmerizing patterns, and what can they tell us about the life cycle of galaxies? The spiral arms you see are not solid structures. They are density waves, regions where stars, gas, and dust pile up temporarily as they orbit the galactic center. Think of it like a traffic jam on a cosmic highway. As material moves through these density waves, it gets compressed, and this compression triggers the birth of new stars. This is why spiral arms often shine with brilliant blue light. That blue comes from young, massive stars, hot and luminous, burning through their fuel at prodigious rates. These stellar nurseries are scattered along the arms like beads on a string. The spiral galaxy is a factory of creation, perpetually renewing itself by forming new generations of stars from the raw materials of its disk. The central bulge of a spiral galaxy tells a different story. Here, in the crowded heart of the galaxy, stars orbit in a more chaotic, random fashion. There is less gas and dust available for star formation, so the bulge is dominated by older stars. These stars shine with a warm yellow or orange light, giving the galaxy's center a golden glow. At the very center of most spiral galaxies, including our own, lurks a supermassive black hole. This dark giant, millions or even billions of times more massive than our Sun, sits quietly at the gravitational heart of the galaxy, holding everything together with its immense pull. It is both the anchor and the architect of the spiral structure we see. In the Hubble Deep Field, we can see spiral galaxies at various distances and therefore at various stages in cosmic history. The nearest spirals appear large and well-defined, with crisp arms and clear structure. But as we look at more distant spirals, those whose light has taken billions of years to reach us, we notice something interesting. They often appear more irregular, more chaotic. Their arms are less well-organized and new. This gives us a clue about how galaxies evolve over time. Young galaxies in the early universe were more turbulent, shaped by frequent collisions and mergers. Over billions of years, they settled down into the elegant, ordered structures we see nearby. The universe is maturing, becoming more organized, finding its shape. Some spiral galaxies have a beautiful feature called a bar structure running through their center. These barred spirals, like our own Milky Way, have a straight band of stars crossing through the nucleus, with the spiral arms emerging from the ends of the bar rather than from the center itself. The bar serves an important function. It channels gas from the outer disk toward the center, fueling star formation in the bulge and feeding the central black hole. It is a cosmic conveyor belt, redistributing material and helping the galaxy evolve. When you look at a barred spiral, you are seeing galactic engineering in action, the invisible hand of gravity sculpting structure on an unimaginable scale. What I find deeply calming about spiral galaxies is their sense of motion and flow. Even though we cannot see them rotating in real time, we know they are spinning, slowly and majestically, completing one revolution every few 100 million years. Stars in the outer arms move more slowly than those closer to the center, creating the distinctive spiral pattern through differential rotation. It is a cosmic ballet, a dance that has been ongoing for billions of years and will continue for billions more. There is something peaceful about that time scale, that sense of eternal motion. These galaxies were spinning before Earth formed. They will still be spinning long after our Sun has died. They represent continuity, permanence, the deep rhythms of the universe. Spiral galaxies like those in the deep field are also surrounded by something we cannot see directly but know must be there. Dark matter. This mysterious substance, which makes up most of the mass of every galaxy, forms an invisible halo extending far beyond the visible disk. We detect its presence through its gravitational effects. The outer stars in spiral galaxies orbit too fast to be held in place by the gravity of visible matter alone. Something else must be there, something that does not emit light but does exert gravitational pull. This dark matter halo is like a cosmic scaffold, a hidden framework that holds the galaxy together and allows it to maintain its beautiful spiral shape. The visible galaxy is just the tip of the iceberg. Every spiral galaxy in the deep field is a complete world unto itself. Within their disks, countless solar systems orbit, planets circle stars, and perhaps, just perhaps, life has emerged to wonder at its own cosmic home. When we look at these distant spirals, we are looking at possibilities. Each one could harbor civilizations, beings looking out at their own night sky, seeing our Milky Way as a faint smudge among thousands of other galaxies. We are not just observing astronomical objects. We are glimpsing potential neighbors across the vast cosmic ocean. The thought is both humbling and exhilarating. We are part of a community of galaxies, a cosmic ecosystem of unimaginable diversity and richness. Not all galaxies in the deep field have the graceful spiral arms we have been admiring. Many appear as smooth, featureless ellipses of light. These are elliptical galaxies, and they represent a very different chapter in the story of cosmic evolution. While spiral galaxies are dynamic factories churning out new stars, elliptical galaxies are ancient cities whose creative days are largely behind them. They contain mostly old stars, with very little gas or dust left to form new ones. They glow with a soft, reddish or yellowish light, the color of aged suns. When you look at an elliptical galaxy, you are looking at the retirement home of the cosmos, a place where the fires of creation have dimmed and a quieter phase of existence has begun. Elliptical galaxies come in a wide range of sizes, from dwarf ellipticals containing only a few million stars to giant ellipticals that dwarf even the largest spirals. The giant ellipticals are among the most massive single structures in the universe, containing trillions of stars and residing at the centers of huge clusters of galaxies. These galactic behemoths formed through multiple mergers, the collision and fusion of many smaller galaxies over billions of years. Each merger stripped away gas and disrupted any spiral structure that might have existed, leaving behind a smooth, spheroidal distribution of stars. In a sense, elliptical galaxies are the product of cosmic violence, the scars of ancient collisions that have healed into peaceful old age. Look closely at the elliptical galaxies in the deep field, and you will notice they lack the blue color of active star formation. Instead, they shine with the light of red giants and other evolved stars. These are suns at the end of their lives, slowly cooling and fading. The lack of blue light tells us that very few, if any, massive young stars are being born in these galaxies. Why? Because elliptical galaxies have used up or lost most of their star-forming gas. During the mergers that created them, tidal forces and supernova explosions heated the gas to such high temperatures that it was blown out of the galaxy entirely, escaping into the vast spaces between galaxies. Without raw material, star formation ceases. The galaxy enters a long, slow fade, but even though elliptical galaxies have stopped making new stars, they are far from inactive. The stars within them are in constant motion, orbiting the galactic center on complex, randomly oriented paths. Unlike the orderly disk of a spiral galaxy where all stars move in roughly the same plane, elliptical galaxies are three-dimensional swarms of stars moving in every direction. Some stars plunge through the center on elongated orbits. Others loop around the outskirts in lazy circles. This chaotic motion is what gives the galaxy its smooth, featureless appearance. There is no preferred direction, no overall rotation to create spiral arms or a disk. It is organized chaos, a perfectly balanced dance of billions of stars held together by gravity alone. At the heart of giant elliptical galaxies lie some of the most massive black holes in the universe. While our Milky Way's central black hole weighs about 4 million times the mass of the Sun, the black holes in giant ellipticals can reach billions of solar masses. These ultra-massive black holes grew fat by consuming gas and stars during the galaxy's violent formation. Some of them are actively feeding even now, pulling in material and releasing enormous amounts of energy as that material falls toward the event horizon. When this happens, the galaxy's core blazes with light and becomes what we call an active galactic nucleus. We can see some of these in the deep field, appearing as points of intense light at the centers of otherwise normal-looking elliptical galaxies. One of the things I find most intriguing about elliptical galaxies is what they represent for the future. Current theories suggest that when two spiral galaxies collide and merge, the result is often an elliptical galaxy. The merger destroys the delicate disk structures and triggers a burst of star formation that quickly exhausts the available gas. What remains is a smooth elliptical composed of the combined stellar populations of both parent galaxies. This means that elliptical galaxies are not just old, they are also fossils of past interactions. They remember, in their structure and stellar content, the collisions that created them. And here is something to ponder. Our own Milky Way is on a collision course with the nearby Andromeda Galaxy. In about 4 billion years, these two spirals will merge, and the result will likely be a giant elliptical galaxy. Does this mean elliptical galaxies are the end state, the final form of galactic evolution? Not necessarily. Even elliptical galaxies can be transformed by future interactions. A small gas-rich galaxy falling into an elliptical can inject new fuel, briefly reigniting star formation. Multiple ellipticals can merge to form even larger ellipticals. And over truly vast timescales, trillions of years from now, when the universe is far older than it is today, even the longest-lived stars in elliptical galaxies will die. The galaxy will fade to darkness, a ghost of its former self, populated only by stellar remnants like white dwarfs, neutron stars, and black holes. But that future is so distant it is almost meaningless to contemplate. For now, elliptical galaxies continue their slow, peaceful existence, monuments to the deep history of the cosmos. When I look at the elliptical galaxies in the Hubble Deep Field, I feel a sense of calm finality. These are structures that have found their equilibrium. They have passed through the fire of creation and destruction and emerged into a stable, unchanging state. There is something peaceful about their smooth forms, their gentle glow. They remind us that even in a universe of constant change and violence, there are places of rest and tranquility. They teach us that endings are not necessarily tragic. They are simply transitions into a different, quieter mode of being. In their ancient light, I find serenity and acceptance, a reminder that all things eventually find peace. Among the carefully ordered spirals and the serene ellipticals, the deep field also contains galaxies that defy easy classification. These are the irregular galaxies, cosmic mavericks that lack any clear structure or symmetry. They appear as chaotic patches of light, asymmetric and disorganized. Some look like exploding fireworks frozen in time. Others resemble clouds torn apart by wind. But do not mistake their lack of classical beauty for lack of importance. Irregular galaxies tell us crucial stories about galactic evolution, especially in the early universe. They show us what galaxies looked like before they had time to settle into the elegant forms we associate with maturity. They are cosmic adolescents, wild and unpredictable, still finding their shape. Irregular galaxies are common in the distant, ancient universe. When we look at the faintest, most distant objects in the deep field, we see many small, irregular blobs of light. These are young galaxies caught in the act of formation less than 1 billion years after the Big Bang. At this early stage, galaxies had not yet had time to organize themselves. They were shaped by turbulent processes, by the infall of matter from surrounding space, by interactions with neighboring proto-galaxies. Star formation was chaotic and episodic, flaring up in random locations as pockets of gas collapsed. The universe at this early time was a wild place, full of energy and violence, nothing like the orderly cosmos we see around us today. But irregular galaxies are not confined to the ancient past. We see them in the modern universe as well. The large and small Magellanic Clouds, satellite galaxies orbiting our own Milky Way, are irregular galaxies. They lack the grand design of spirals, appearing instead as messy collections of stars and gas. Why? Because they are being gravitationally disrupted by their close passage to our galaxy. Tidal forces from the Milky Way are pulling on them, stretching them out, stripping away their gas. This interaction prevents them from maintaining any stable structure. They are galaxies caught in the grip of a larger neighbor, slowly being torn apart and consumed. Eventually, billions of years from now, they will merge completely with the Milky Way, adding their stars to our galaxy's halo. Irregular galaxies are often sites of intense star formation. Because their gas is not settled into a stable disk like in spiral galaxies, it can undergo rapid, chaotic collapse in multiple locations simultaneously. This creates scattered regions of vigorous starbirth, each one blazing with the light of young, hot stars and illuminating nearby nebulae with brilliant pinks and blues. Some irregular galaxies are undergoing what astronomers call a starburst, a period of exceptionally rapid star formation that cannot be sustained for long. During a starburst, a galaxy can form stars at a rate hundreds or thousands of times faster than a normal spiral galaxy. It is as if the galaxy is burning through its fuel reserves in a final, glorious blaze. What triggers these starbursts? Often it is a collision or close encounter with another galaxy. When two galaxies pass near each other, their gravitational interaction compresses gas clouds, triggering massive waves of star formation. Sometimes one galaxy plunges directly through another, creating a spectacular cosmic collision. The stars themselves almost never collide. Space is too vast and stars too small. But the gas clouds do collide, shock and compress, sparking new stellar nurseries. The result can be a transformed galaxy, no longer recognizable as its former self. These collisions are violent on cosmic scales, but take millions of years to unfold. We see them in the deep field as galaxies with disturbed, irregular shapes and bright knots of recent star formation. Irregular galaxies challenge our aesthetic expectations of what a galaxy should look like. We are drawn to symmetry, to order and pattern. But the universe does not care about our aesthetic preferences. It creates beauty in chaos as well as in order. When I look at an irregular galaxy, I see a different kind of beauty, the beauty of raw energy and spontaneity. These are galaxies that have not been tamed by time, that still retain their primordial wildness. They remind us that the universe is not a static, perfect clockwork. It is dynamic, messy, unpredictable. And there is something thrilling about that, something that makes the cosmos feel alive and vibrant rather than cold and mechanical. Some irregular galaxies show evidence of recent or ongoing interactions in more subtle ways. Tidal tails, long streams of stars pulled out of the galaxy by gravitational forces, stretch across space like cosmic spider silk. Bridge structures of gas and stars connect galaxies that are in the process of merging. These features tell us that the galaxies we see are not isolated islands, but participants in a complex gravitational dance. They influence each other, shape each other, sometimes merge with each other. The universe on the scale of galaxies is a busy, interconnected place. Every galaxy has neighbors, and those neighbors matter. Their gravitational pulls, their gas reservoirs, their future collisions, all play a role in determining what each galaxy will become. The irregular galaxies in the Hubble Deep Field remind us of an important lesson. The categories we create, the boxes we use to organize our understanding, are ultimately human constructs imposed on a universe that does not follow our rules. Not every galaxy fits neatly into spiral or elliptical. There is a whole spectrum of forms, a continuum from perfect order to complete chaos, and every point along that spectrum has its own story to tell. When we embrace this diversity, when we appreciate the full range of galactic morphologies, we come closer to understanding the true complexity and richness of the cosmos. We learn to find beauty in the unexpected, meaning in the irregular, wonder in what does not conform. One of the most striking features of the Hubble Deep Field is the incredible range of colors displayed by its thousands of galaxies. Some glow with brilliant blue light, others shine with deep red or warm orange hues. Still others blend multiple colors in complex patterns. But these colors are not arbitrary. They are not decorative. Each color tells us something fundamental about the galaxy we are observing. The color of a galaxy reveals its age, its star formation rate, its chemical composition, and its distance from us. When we learn to read this cosmic color code, the deep field transforms from a pretty picture into a detailed map of galactic evolution across time and space. Let us decode this language of light together. Blue galaxies are young and vigorous. The blue color comes from hot, massive stars that have formed recently. These stellar giants burn incredibly hot, with surface temperatures reaching tens of thousands of degrees. At these temperatures, they emit most of their light in the blue and ultraviolet parts of the spectrum. Because massive stars have such short lives, only a few million years, their presence in a galaxy tells us that star formation is happening right now. When you see a blue galaxy in the deep field, you are looking at a cosmic nursery, a place where clouds of gas are actively collapsing to form new generations of stars. The galaxy is in its creative phase, its youth, burning bright with the energy of birth. Red galaxies, by contrast, are old and quiet. The red color comes from cooler stars, red giants and red dwarfs that have much lower surface temperatures than their blue counterparts. These stars emit most of their light in the red and infrared parts of the spectrum. A galaxy that appears red has exhausted most of its gas supply and is no longer forming significant numbers of new stars. The massive blue stars that once shone brightly have long since died, leaving behind only the lower mass, longer-lived stars that burn red. When you see a red galaxy, you are looking at a place that has passed its creative peak, a cosmic city whose busiest days are in the past. It is entering a long, slow twilight. But there is another reason. A galaxy might appear red, and this one has to do with the expansion of the universe itself. As light travels through expanding space, its wavelength gets stretched. Blue light can be stretched so much that it becomes red light by the time it reaches us. We call this cosmological redshift, and it affects all light from distant galaxies. The more distant the galaxy, the more its light has been redshifted. So when we see a very red galaxy in the deep field, we have to ask ourselves which effect we are seeing. Is it an intrinsically old red galaxy nearby? Or is it actually a younger blue galaxy so far away that its light has been redshifted into the red? Astronomers have techniques to distinguish these cases, but it is a beautiful reminder that observation is interpretation. Some galaxies show a mix of colors, blue regions coexisting with red ones. These are typically spiral galaxies where different parts of the galaxy are in different evolutionary stages. The spiral arms, rich in gas and dust, blaze blue with new star formation. The central bulge, depleted of gas, glows red with old stars. This color gradient reveals the internal structure and history of the galaxy. We can map out where stars are being born, where they are aging, and where they have already died. The galaxy becomes a living history book. each color corresponding to a different chapter in its long story. These multicolor galaxies are particularly beautiful, combining the vibrancy of youth with the serenity of age. The colors of galaxies also tell us about their chemical composition. Stars are born from clouds of gas that contain not just hydrogen and helium, but also heavier elements created by previous generations of stars. These elements, which astronomers call metals even though they include oxygen, carbon, nitrogen, and others, affect the color of starlight. A galaxy rich in metals will have subtly different colors than a metal-poor galaxy. This is especially important when looking at ancient, distant galaxies in the deep field. These early galaxies formed from nearly pristine gas containing almost no heavy elements. Their first stars were pure hydrogen and helium, and they shone with a distinctive color. As successive generations of stars lived, died, and enriched the gas, the colors of subsequent stars changed. There is something deeply moving about the fact that we can read so much information from color alone. Think about it. Light leaves a distant galaxy, travels for billions of years across expanding space, and finally enters the detector on Hubble. From the color of that light, we can deduce the galaxy's age, its star formation history, its chemical composition, and its distance. We can tell whether it is actively creating new stars or slowly fading into old age. We can estimate how long ago its light began its journey toward us. All of this from color. It is like reading a biography written in light, a story told across the electromagnetic spectrum. The universe is communicating with us, and when we learn its language, every photon becomes a word in an epic poem. When I spend time just looking at the colors in the deep field, not analyzing them but simply appreciating them, I am struck by the sheer aesthetic beauty of the image. It looks like abstract art, like paint splattered on a cosmic canvas. Blues and reds and golds and whites arranged in no apparent pattern but creating a composition that feels balanced and whole. This is not design. No artist chose where to place these colors. They emerged naturally from the physics of stars, galaxies, and cosmic expansion, and yet the result is breathtakingly beautiful. It reminds me that the universe has its own aesthetic, its own sense of beauty that exists independently of human observation. We did not create this beauty. We are merely privileged witnesses to it. If you examine the Hubble Deep Field carefully, you might notice that galaxies are not distributed randomly across the image. In some regions, they cluster together, forming small groups and associations. These are not chance alignments. These galaxies are gravitationally bound to each other, forming cosmic communities called galaxy clusters. Just as stars gather together to form galaxies, galaxies themselves gather together to form larger structures. These clusters are among the largest bound objects in the universe, containing hundreds or even thousands of individual galaxies, all orbiting a common center of mass. They are cities in space, metropolises of galaxies connected by invisible threads of gravity, sharing the same vast region of the cosmic web. Galaxy clusters are held together by enormous amounts of mass. But here is something remarkable. When astronomers add up all the visible matter in a cluster, all the stars in all the galaxies, it accounts for only about 2% of the total mass needed to hold the cluster together. Another 12% or so is hot gas that fills the space between galaxies, glowing faintly in X-rays. But the remaining 86% is dark matter, invisible and detectable only through its gravitational effects. This dark matter forms a massive halo that permeates the entire cluster, providing the gravitational glue that keeps everything bound. The visible galaxies are like fireflies, illuminating a vast, dark forest. The forest itself is invisible, but we know it must be there. The environment within a galaxy cluster is very different from the isolation of field galaxies. Galaxies within clusters are in constant gravitational interaction with their neighbors. They orbit the cluster center at high speeds, sometimes plunging through the central regions where the density of galaxies is highest. During these passages, they can experience ram pressure, a drag force created by moving through the hot gas that permeates the cluster. This ram pressure can strip away a galaxy's own gas, shutting down star formation and transforming a blue spiral into a red gas-poor galaxy. The cluster environment is harsh, hostile to star formation. Galaxies that join a cluster often find their creative days are over. The central regions of rich galaxy clusters are often dominated by a single massive elliptical galaxy called the brightest cluster galaxy. This cosmic giant sits at the bottom of the cluster's gravitational potential, growing ever larger by cannibalizing smaller galaxies that wander too close. It is a galactic predator, feeding on its neighbors, growing fat on their stars. Over billions of years, it can accumulate the mass of dozens or hundreds of smaller galaxies. The brightest cluster galaxy is often surrounded by a halo of globular clusters, dense balls of old stars numbering in the thousands. It is the king of its domain, the most massive and luminous galaxy in the cluster, testament to billions of years of gravitational dominance. Galaxy clusters act as gravitational lenses, bending and magnifying the light from even more distant galaxies behind them. Einstein's general relativity tells us that mass warps space-time, and light follows this warped geometry. When light from a background galaxy passes near a massive cluster, its path is bent, causing the background galaxy's image to be distorted, stretched, or multiplied. We see arcs and rings of light around clusters, which are actually highly magnified images of distant galaxies. This gravitational lensing turns clusters into natural telescopes, allowing us to see objects that would otherwise be too faint and distant to detect. The cluster uses its mass to magnify the universe behind it, giving us a glimpse of the most ancient galaxies. The hot gas that fills galaxy clusters, though invisible to optical telescopes, tells its own fascinating story. This gas, heated to tens of millions of degrees by the energy of galaxy motions and by material falling into the cluster, glows brightly in X-rays. When we observe clusters with X-ray telescopes, we see them filled with this diffuse hot atmosphere. The shape and distribution of this gas reveals the history of the cluster. Smooth, symmetric gas distributions indicate a relaxed cluster that has not undergone recent major mergers. Disturbed, asymmetric distributions reveal that the cluster is still forming, still experiencing violent collisions as smaller groups fall into it. These collisions release enormous amounts of energy, heating the gas and creating shock waves that ripple through the cluster. Galaxy clusters are also cosmic laboratories where we can study dark matter and test our theories of gravity. Because clusters contain so much mass concentrated in a relatively small volume, their gravitational effects are strong and measurable. By observing how galaxies move within clusters, how light is bent around clusters, and how the hot gas is distributed, we can map out the distribution of dark matter. What we find is that dark matter dominates the cluster, forming a smooth halo that extends far beyond the visible galaxies. This dark matter halo is not uniform but has structure, concentrations, and voids that trace out the hidden architecture of the cosmic web. Clusters sit at the intersections of dark matter filaments, nodes in a vast network that spans the universe. When I contemplate galaxy clusters, I am reminded of the fractal nature of the universe. Planets orbit stars. Stars gather into galaxies. Galaxies collect into clusters. And clusters themselves form even larger structures called superclusters. Vast assemblages containing dozens of clusters and stretching hundreds of millions of light years across space. At every scale, we see hierarchy and organization, structure emerging from gravity's patient work over cosmic time. It is beautiful and elegant, this nested organization, and it gives us perspective. Our entire Milky Way galaxy, with its hundreds of billions of stars, is just one member of a larger community. We are part of something greater, connected to cosmic structures that span unimaginable distances. We belong to the universe in ways we are only beginning to understand. Let us now turn our attention to one of the most profound aspects of the Hubble Deep Field. This image is not just a map of space. It is also a map of time. Because light travels at a finite speed, when we look at distant objects, we are seeing them not as they are now, but as they were when their light began its journey. The deep field contains galaxies at every distance, from relatively nearby to extraordinarily far away, and thus shows us galaxies at every age, from the present day to the ancient past. In a single image, we can trace the entire history of galactic evolution. We can watch the universe grow up, transform from the chaotic early cosmos into the structured universe we inhabit today. We are cosmic archaeologists, excavating time itself. The nearest galaxies in the deep field are only a few 100 million light-years away. Their light has been traveling for a few 100 million years, so we see them as they appeared in the relatively recent past. These galaxies look much like galaxies in our local neighborhood. They are well-formed, mature structures with clear morphologies. Spiral galaxies have well-defined arms. Elliptical galaxies are smooth and symmetric. Star formation proceeds at a moderate pace. This is the modern universe, the present epoch of cosmic history. But as our eyes move to fainter, more distant galaxies, we begin to see changes. The galaxies start to look different. They become smaller, more irregular, more chaotic. We are looking deeper into the past, seeing galaxies as they were billions of years ago. At intermediate distances, say 5 to 8 billion light-years away, we see galaxies from the universe's middle age. This was a time when the cosmos was roughly half its current age. Star formation was more vigorous than it is today. Galaxies were growing rapidly, building up their stellar populations. We see more blue galaxies, more irregular forms, more evidence of mergers and interactions. The universe at this epoch was a busier, more active place than the universe we inhabit now. Galaxy collisions were more common because galaxies were closer together in the smaller, denser universe of the past. This was the peak era of cosmic star formation, when the universe was converting gas into stars at the highest rate in its history. It was the cosmic baby boom. The most distant galaxies in the original Hubble Deep Field, those whose light has traveled for 10 billion years or more, show us the universe in its youth. These ancient galaxies appear as small, faint, irregular blobs. They are the building blocks of larger galaxies, small fragments that will eventually merge to form the massive galaxies we see nearby. The universe at this epoch was only a few billion years old, just emerging from the cosmic dark ages that followed the Big Bang. The first generations of stars were enriching the cosmos with heavy elements for the first time. Galaxies were assembling from smaller pieces. It was a time of construction, of growth, of transformation. The universe was finding its structure. The Hubble Deep Field reaches back to when the universe was less than 1 billion years old. But it does not quite reach the very beginning. There is a frontier beyond which even Hubble cannot see, a region of space and time so distant that the light has not yet had time to reach us, or has been redshifted into wavelengths that Hubble cannot detect. This is the realm of the first galaxies, the first stars, the epoch of reionization when the universe transitioned from neutral hydrogen to the ionized plasma we see today. To probe this era, we need more powerful instruments. And that is why subsequent missions like the James Webb Space Telescope were built to push back the curtain and reveal the very first light in the cosmic dawn. What I find most moving about the deep field's temporal depth is the realization that we are seeing cause and effect across billions of years. The small, irregular galaxies we see in the distant past are the ancestors of the large, mature galaxies we see nearby. We can watch the family tree of galaxies unfold before our eyes. That small blue blob 10 billion years in the past grew, merged with its neighbors, and eventually became a massive spiral like the Milky Way. Every nearby galaxy has a history, a lineage, a story of growth and transformation. And we can read that story by looking at their ancestors in the deep field. It is like having a time-lapse movie of galactic evolution compressed into a single frame. The ability to look back in time is unique to astronomy. A biologist cannot watch an animal's ancestors evolving. A geologist cannot observe the formation of mountains as they happened. But astronomers can see the past directly. We can witness events that occurred billions of years ago simply by looking at distant objects. This temporal perspective is one of astronomy's greatest gifts. It allows us to answer questions about origins, about how things came to be. Where did galaxies come from? How did they form? How have they changed over time? The deep field provides answers to these questions not through theory or simulation, but through direct observation. It shows us the past as it actually was, frozen in ancient light. There is something both humbling and exhilarating about being able to look backward across most of the age of the universe. It puts our own existence into perspective. The cosmos has been evolving for nearly 14 billion years. Stars have been born and have died. Galaxies have collided and merged. The elements in our bodies were forged in stellar furnaces over countless generations. We are latecomers to this cosmic story, appearing only in the most recent chapter. And yet, we have the remarkable ability to look back and understand where we came from, to trace our lineage all the way back to the Big Bang. The deep field is a mirror showing us our own deep history, our connection to the ancient past. We are children of the universe, and the deep field shows us our family album. The original Hubble Deep Field, captured in 1995, was such a scientific and cultural success that it spawned a legacy of follow-up observations. Astronomers realized they had stumbled upon a powerful technique for studying the distant universe. Why not repeat the observation in different parts of the sky? Why not observe even longer, go even deeper? And why not use different wavelengths to reveal aspects of the universe invisible in optical light? Thus began a series of deep field observations that have continued for decades, each one pushing the boundaries of what we can see, each one revealing new layers of cosmic structure. It was the beginning of a new era in observational cosmology. In 1998, Hubble observed the southern hemisphere counterpart to the original deep field, creating the Hubble Deep Field South. This confirmed that the original observation was not a fluke. The southern deep field showed similar numbers of galaxies, similar types, similar distributions. The universe is remarkably uniform on large scales. No matter which direction we look, we see roughly the same cosmic structure. This isotropy is one of the foundational observations supporting the Big Bang model. The universe does not have a center or an edge. It looks the same in all directions. The deep field south gave us confidence that what we learned from the original observation was representative of the universe as a whole. Then came the Hubble Ultra Deep Field in 2004, an observation that went even deeper than the original. This time, Hubble stared at a patch of sky for over 11 days of exposure time, accumulating light from the faintest, most distant objects ever seen. The ultra-deep field revealed nearly 10,000 galaxies in an area even smaller than the original deep field. It pushed back the frontier, showing us galaxies from when the universe was only 700 million years old. These were among the first galaxies to form after the Big Bang, primitive structures emerging from the primordial darkness. The image was stunning, a deeper glimpse into the abyss than humanity had ever achieved. In 2012, Hubble created the E-Extreme Deep Field, or XDF, combining data from multiple observations to create the deepest image of space ever made at that time. The XDF represents over 2 million seconds of exposure time, more than 23 days of cumulative observation. It shows galaxies that existed just 450 million years after the Big Bang, pushing tantalizingly close to the cosmic dawn. Some of the faintest galaxies in the XDF are so distant that one pixel in the image covers hundreds of light years. These are not mere points of light. They are entire galaxies, vast collections of billions of stars compressed into single pixels because of their incredible remoteness. The scale is almost incomprehensible, but Hubble's capabilities have limits. Its mirror is relatively small, and its instruments are primarily sensitive to optical and near-infrared light. To go even deeper, to see the very first galaxies, we needed a more powerful telescope. That telescope is the James Webb Space Telescope, launched in 2021. Webb has a much larger mirror and observes primarily in the infrared, perfect for detecting heavily redshifted light from the earliest galaxies. Within months of beginning operations, Webb captured its own deep field images, revealing galaxies that existed just 300 million years after the Big Bang. These are the most distant galaxies ever observed, light from the very edge of the observable universe, the cosmic horizon itself. Webb's deep field images are stunning in their own right, showing galaxies that are impossibly distant and yet remarkably detailed. Because Webb observes in the infrared, it can see through dust that blocks optical light. It reveals hidden star formation, obscured galaxy centers, and structures invisible to Hubble. The galaxies Webb sees from the early universe are surprisingly large and mature, more organized than theoretical models predicted. This is causing astronomers to revise their understanding of how quickly galaxies could form and grow. Science is a process of constantly refining our models as new data comes in. Webb is providing that new data, challenging us to think differently about the early universe. The legacy of the Hubble Deep Field extends beyond the images themselves. It changed how astronomers think about using telescopes. Before the Deep Field, long integrations on faint targets were considered risky and unconventional. After its success, deep surveys became routine and recognized as essential tools for understanding cosmology. The Deep Field inspired an entire generation of astronomers and captured the public imagination in ways few scientific images have. It became an icon, a cultural touchstone, a symbol of humanity's quest to understand our place in the universe. It has appeared in countless documentaries, textbooks, planetarium shows, and popular media. It has inspired wonder in millions of people around the world. The story of the Deep Field continues. Even now, as you listen to these words, new deep field observations are being planned and executed. Next-generation telescopes, both in space and on the ground, will push even deeper, revealing galaxies even more distant and ancient. There is always a frontier, always something beyond what we can currently see. And that is beautiful. Means the universe will never cease to surprise us. There will always be new discoveries, new wonders, new mysteries to explore. The Deep Field taught us that when we look at what appears to be nothing, we find everything. It taught us to point our telescopes boldly into the darkness and trust that the universe will reveal its secrets. That lesson remains as vital today as it was in 1995. Let us pause now to truly comprehend the scale of what the Hubble Deep Field represents. Numbers can be abstract, and when they become very large, they lose their meaning to our human minds. But understanding the scale is crucial to appreciating the profound message of the deep field. We have said that the deep field covers a tiny patch of sky, about 1/24 millionth of the celestial sphere. We have said it contains about 3,000 galaxies. But what does this really mean? Let us take a journey through the mathematics of cosmic abundance and try to grasp, really grasp, the incomprehensible vastness of the universe revealed by this single image. Imagine you are standing outside on a perfectly dark night, far from city lights. How many stars can you see with your naked eye? Under the best conditions, you can see roughly 6,000 stars across the entire sky. That is the sum total of stellar points visible to unaided human vision. Now, consider this. The Hubble Deep Field contains 3,000 galaxies in a region 1/24 millionth the size of the sky. Each of those galaxies contains at least hundreds of millions of stars. Many contain hundreds of billions. The deep field alone shows us more stars than you could count in 1,000,000,000,000 lifetimes. And it represents only a tiny fraction of the observable universe. The disparity between what we can naturally perceive and what actually exists is almost unimaginable. Let us try another approach. If we extrapolate from the deep field to the entire sky, we estimate the observable universe contains roughly 100 billion to 200 billion galaxies. Now, let us say the average galaxy contains about 100 billion stars. That means the total number of stars in the observable universe is approximately 10 billion trillion. That is a 1 followed by 22 zeros. To put this in perspective, there are more stars in the universe than there are grains of sand on all the beaches on Earth. More stars than there are cells in every human being who has ever lived. More stars than seconds have passed since the universe began. The number is so vast that it exceeds our capacity to truly comprehend. But even that is not the full story. Each star is a potential sun for a family of planets. Many stars have planetary systems. The Kepler mission taught us that planets are common, possibly more common than stars themselves. If even a fraction of stars have planets, and even a tiny fraction of those planets are suitable for life, the potential number of life-bearing worlds becomes staggeringly large. The Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy alone, involves multiple factors that are highly uncertain. But even conservative estimates suggest we may not be alone. The deep field, showing us the true abundance of galaxies and thus stars and thus planets, makes the possibility of extraterrestrial life not just plausible but almost inevitable. The distances involved are equally mind-expanding. The nearest galaxies in the deep field are hundreds of millions of light years away. The most distant are over 13 billion light years away. A light year is the distance light travels in 1 year, moving at 300,000 kilometers per second. That is nearly 10 trillion kilometers. Even the nearest galaxy in the deep field is millions of trillions of kilometers away. If you could travel at the speed of light, impossibly fast by any human standard, it would take you hundreds of millions of years to reach that nearby galaxy. With current technology, it would take trillions of years. The distances are so vast, they make space travel between galaxies seem not just difficult, but effectively impossible. And yet, despite these incomprehensible distances, we are connected to those distant galaxies through light. Photons that left those galaxies billions of years ago have traveled across the expanding universe to reach us. They have threaded through space and time, avoiding every obstacle to arrive at Earth and be captured by Hubble's mirror. In a very real sense, those distant galaxies are reaching out to us, communicating with us through the universal language of light. We are in contact with the deep universe. It is speaking to us, telling us its history, revealing its structure. All we have to do is listen, to pay attention to the messages encoded in the light. Astronomy is the art of reading these cosmic messages. The scale of the universe revealed by the deep field can provoke different reactions. Some people feel overwhelmed, even frightened by the vastness. It can make us feel insignificant, tiny beyond measure. And in a literal physical sense, We are tiny. Earth is a mote of dust in a cosmic ocean. But I prefer to think about it differently. Yes, we are small, but we are also capable of comprehending this vastness. We are the universe's way of knowing itself. Through our telescopes and our science, through our curiosity and our imagination, the cosmos looks back at its own grandeur. We are small in size, but infinite in potential. Our consciousness is the universe contemplating its own existence. That is not insignificance. That is profound significance. When I truly sit with the scale revealed by the deep field, I feel a sense of peaceful humility. My day-to-day concerns, my worries and anxieties, they do not disappear, but they are put in perspective. I am reminded that I am part of something vast and ancient and wonderful. The same atoms that make up my body were forged in stars. The light that entered my eye at birth began its journey billions of years ago from distant galaxies. I am not separate from the universe. I am an integral part of it, a way for the cosmos to experience and understand itself. This realization brings me a deep sense of connection and peace. I hope it does the same for you. The deep field is not just an image. It is a mirror, reflecting our place in the infinite cosmos. As our journey through the Hubble Deep Field draws toward its close, I want to reflect on the deeper meanings this image holds. Beyond the scientific discoveries, beyond the technical achievements, the deep field delivers a message to humanity. It is a message about our place in the universe, about the nature of existence, about what it means to be conscious beings in an incomprehensibly vast cosmos. Different people hear different messages when they look at the deep field. For me, the primary message is one of perspective. When we truly absorb what this image shows us, it fundamentally changes how we see ourselves and our world. It invites us to think differently, to feel differently, to live differently. The deep field teaches humility. How can we remain arrogant or self-important when we see that our entire galaxy is just one among hundreds of billions? That our planet is a microscopic speck orbiting an ordinary star in an unremarkable galaxy? Our disputes, our divisions, our conflicts over territory or ideology or resources, they all seem small and petty when viewed from the cosmic perspective. This is not to say that human concerns do not matter. They do matter. They matter infinitely to us. But the deep field reminds us to keep things in proportion. We are part of something so much larger than ourselves. That realization can be liberating. It can free us from excessive self-importance and open us to wonder. But the deep field also teaches us about connection. We are not separate from the universe. We are made of the same matter, governed by the same laws, participating in the same cosmic story. The iron in your blood was forged in the heart of a dying star. The calcium in your bones was created in a supernova explosion. You are literally made of stardust, cosmic material, recycled through generations of stellar alchemy. When you look at a galaxy in the deep field, you are looking at a distant relative, different in form but related through the fundamental unity of the cosmos. We are all children of the same universe, members of the same cosmic family. This realization can foster a sense of kinship not just with other humans, but with all of existence. The deep field inspires wonder, and wonder is essential to a meaningful life. Wonder is the feeling of awe and curiosity in the face of something vast and beautiful and mysterious. It is what we feel when we encounter something that exceeds our expectations, that surpasses our ability to fully comprehend. The deep field elicits wonder because it shows us that reality is far stranger and more magnificent than we imagined. There are more things in heaven and earth than are dreamt of in our philosophies. When we allow ourselves to feel wonder, we open ourselves to growth. We become students of the universe, eager to learn its lessons. Wonder keeps us humble, curious, and alive to beauty. For me personally, the deep field is a source of comfort during difficult times. When I am struggling with challenges, when the weight of daily life feels heavy, I turn to images like the deep field. They remind me that my problems, as real as they are to me, are temporary and local. The universe continues its grand dance regardless of my personal struggles. Blessing, not depressing. It is freeing. It allows me to put my difficulties in perspective, to realize that I am part of something larger that will continue long after I am gone. There is peace in that realization. It helps me let go of anxiety about things I cannot control and focus on what I can do in the present moment. The deep field also speaks to our responsibility as conscious beings. We have been given, through evolution and cosmic fortune, the ability to understand the universe. We can look at an image like the deep field and comprehend what it represents. We can trace the history of cosmic evolution, understand the physics of stars and galaxies, and contemplate our place in this vast scheme. This is an extraordinary gift, and with it comes responsibility. We are the universe's consciousness, its way of knowing itself. We have a duty to preserve that consciousness, to protect the fragile biosphere that sustains it, and to continue the quest for understanding. The deep field reminds us that we are stewards of something precious and rare. I find it deeply moving that the deep field exists at all. Think about the chain of events necessary for this image to come into being. The universe had to evolve for billions of years. Stars had to form and die. Planets had to coalesce. Life had to emerge on at least one of those planets. That life had to evolve intelligence. That intelligence had to develop science and technology. We had to build rockets and launch a space telescope. We had to point that telescope at an empty patch of sky and wait patiently for light. And then we had to process and share the image so that anyone, anywhere could look at it and wonder. The deep field is a testament to human curiosity, ingenuity, and perseverance. It represents the best of what we can achieve when we work together toward understanding. Finally, the deep field reminds us that there is always more to discover. What we see in the image is extraordinary, but it is only a beginning. Each of those 3,000 galaxies could be studied in detail for years. Each one has its own history, its own population of stars, its own potential for harboring life. Beyond what we can see lie even more distant galaxies, regions of space we have not yet observed. And beyond the observable universe lies the truly unknowable, regions so distant that their light will never reach us. The universe is larger than we can ever fully know, and that mystery is beautiful. It means the sense of wonder will never end. There will always be new frontiers to explore, new questions to ask, new mysteries to ponder. The deep field is not an answer. It is an invitation to keep asking. Our hour together exploring the Hubble Deep Field has come to an end, but the image itself remains, an eternal testament to the grandeur of the universe and the power of human curiosity. The next time you look up at the night sky, remember what you have seen here. That darkness between the stars is not empty. It is filled with galaxies, billions of them, each containing billions of stars. You are looking at infinity. You are part of infinity. What will you do with this knowledge? How will it change how you see yourself and your place in this magnificent cosmos? These are questions only you can answer. Thank you for joining me on this journey into the deep field. May you find wonder in the darkness and peace in the infinite.